Okay, this is Professor Birdsong. I'm going to do lesson 25. We're going to talk about experimental Bode diagrams today. I tried to do the lecture live, but I had a bad internet connection and it kept dropping. So I decided I'm going to just record it and post the video afterwards. And hopefully on our next lesson, the internet's working better. Okay, I spent a few minutes reviewing this problem from before. Here we were trying to draw the Bode diagram of a complex transfer function with a differentiator, finite poles, and finite zero and complex poles. So let's say we dissect the transfer function to its parts. We had to normalize it. Remember, the normalization process is you factor out each coefficient, so there's a 1 in the lowest coefficient. So here we'd have 8.3 over 20 times s over 8.3 plus 1 divided by s squared over 20 plus 3 over 20 s plus 1. Okay, so there's a normalization, and then we factor out this gain, and that gain then goes over here as a sort of a separate calculation. So we're going to draw all the parts, the differentiator, the zero, and the poles, normalized so that they all start at 0 at the origin. That just makes it easier to draw. Okay, and so we did that. We drew the three parts. The differentiator looked like this. Right, it just keeps increasing at a rate of 20 dB per decade everywhere. The complex poles, the finite zero starts at 0 dB, and then it breaks up at the value of the zero, 8.3 units per second. And then the complex poles start at 0 dB, and then they break down at 40 dB per second, and the transition happens at the natural frequency. And then we use graphical addition to add those three. I drew them in three different colors, so we could say we add the blue, green, and black lines together. Well, the black and the green lines are 0 for low frequency, so the sum just follows along the blue line. Right? And so it does that until we hit the first break frequency, and then it goes down because the complex poles are contributing minus 40 dB per decade, and then it straightens out because now the finite zero contributes plus 20 dB per decade, and so that's what we get. Okay, and then the phase is similar. We draw the phase diagram for each component. We've got the phase of the differentiator as a constant 40 or 90 degrees everywhere at all frequencies. Okay, the differentiator starts at 0 and then breaks down to minus 90 across 2 decades around the value of the the zero breaks up. So it starts at 0. The 0 gives us positive phase, so it goes from 0 to plus 90 degrees phase, and that happens over 2 decades around the value of 0, 8.3. Okay, and then the complex poles start at 0, and then they break down they go across 180 degrees over 2 decades, like that. And then we use graphical addition to add those three together, so we get the red line like that. Okay, so that's everything we did last time. I went through it slower in more detail last time, but there's a few things I want to point out here. For one, notice that we have a low frequency slope here. We have a low frequency slope of plus 20 dB per decade. Okay, and that's because we have the differentiator in the transfer function, right? So the differentiator always gives us a slope of 20 dB per decade, no matter how low we go. So if we went another decade, we started at 0.1, but if we went another decade down, this slope would just keep on going down, 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 down like that. Okay, so when we have a differentiator, we always have a low frequency slope of 20 dB per decade. And if we have an integrator, an s in the denominator, then we'd have a low frequency slope of minus 20 dB per decade. Okay, so that's one thing to note, is that low frequency slope is the result of an integrator or a differentiator. The other issue with that is there's no DC gain when we have a low frequency slope. Okay, remember the DC gain is the gain of the transfer function at low frequency, but because of the differentiator in the transfer function, the lower we go in frequency, the smaller the transfer function magnitude gets, and it never flattens out. Okay, so it just keeps getting lower and lower and lower. So there is no DC gain. So that's an issue for some of the calculations we do, and we'll see that later on. Okay, also we should talk about the phase. There's a couple of interesting things to note. Notice that low frequency has a phase of plus 90. It just starts at 90 degrees phase, and that's also because of the differentiator. Right? The differentiator contributes a phase of plus 90 everywhere. So no matter how low of a frequency we go, we're always going to have 90 degrees phase, whereas the other two functions start at 0 phase. Okay, so that's the effect of the differentiator. If we had an integrator, then it would start at minus 90 degrees at low frequency. Okay, the other thing to note is that it ends at 0 degrees phase at high frequency. And that's something we can predict because if you look at the transfer function up here, we can see that there's a s squared in the numerator and an s squared in the denominator. So there's an equal number of s's in the numerator and the denominator. So if we go to a high enough frequency, once we get past the breakpoints of all the dynamics, then everything flattens out, and the phase from the zeros in this case will cancel out the phase from the poles and end up with 0. So we can always predict what the final phase will be by figuring out the difference between the number of poles and the number of zeros. We'll always have equal or more poles because it's got to be a proper transfer function. Okay, and it's always got to be in increments of 90 degrees, right? Because poles and zeros each contribute 90 degrees of phase. So you'll see in the example problem, I ended exactly at 0 degrees phase. Probably if you did this on your own, you didn't end up at 0 degrees phase. It's kind of hard to do. You got to get all of these slopes exactly right and the intersects exactly right to do it. I got to tell you, I cheated because I knew it ended at 0, so I made sure I did it carefully and sort of steered the answer to end at the right phase. But you can do that also because you can look at the transfer function and predict the high frequency phase by computing the difference between the number of s's in the denominator and in the numerator. Okay, so that's just a review of that example problem. It's a pretty challenging problem, but that's good in terms of drawing the Bode diagram. Now we want to move forward and look at the next problem. Now we're going to flip it. We're going to reverse that process, and the idea is now, given the Bode diagram, we want to try to figure out the transfer function. And the way we do this is by the work we've done before, by taking the transfer function and drawing the Bode diagram. That gives us knowledge about the characteristics of these Bode diagram pieces. So when we look at it, we should recognize them. Okay, so if you look at this diagram, you see a hump here in the magnitude plot, and that should make you think about a second order poles, right? Like a mass spring damper system. It starts at 0. Oh, it's got 0 slope at low frequency, so that tells us, right, 0 slope at low frequency. That tells us there's no integrators or differentiators. No integrator or differentiators, right? Because that would give us a slope of 20, plus or minus 20 degrees per decade. It also starts at 0 phase, so that tells us there's no integrators as well. Okay, so that's good evidence, so no integrators. So we know it's got a second order transfer function because it starts at 0 and then dives down quickly. But it does not go to 180, right? If it were a second order transfer function, then we'd expect it to keep going down to minus 180 degrees. There's something else going on here, right? Instead, what the phase does is it starts to go down, but then it comes up over here like that. And so what could do that? And we see that the final phase is minus 90 degrees, okay? So that final phase tells us 90 degrees. There's one more s in the denominator than the numerator, okay? So those are all clues that help us think what the transfer function should be. So at this point, we can write down our model of the transfer function. I'm going to do it all symbolically. So we have second order poles, s squared plus 2 zeta omega n s plus omega n squared, okay? But there's got to be, right now I've got 2 s's in the denominator and no s's in the numerator. That can't be it. There's got to be additional dynamics that make the phase go up 90 degrees, and that's got to be a finite 0. So there must be a s plus z in the numerator like that to account for that. Okay, so that's good. And then the last thing I'll do is throw in a gain k, okay, because probably the gain is not just z over omega n squared. There might be some other gain, so it's just good practice to throw a gain k in there just in case. All right, so that's our model of the transfer function, and we can sort of go and make sure it all makes sense and it fits all the right characteristics with the magnitude and the phase diagram, and I think we're pretty good here. Okay, so now the next step is to figure out the parameters. So really there's a list of parameters, right? There's omega n, there's z, there's zeta, and there's k. So there's 4 parameters in this transfer function, and all I have to do is figure them out and try to estimate them from the graph. Okay, so let's see, let's start with omega n. Okay, well, I do see a peak right here. Okay, and that looks like it's at about, let's see, 1, 2, 3, 4, 5. So I'm going to write omega p is equal to 5 radians per second. Okay, remember the natural frequency doesn't necessarily occur exactly at the peak. Okay, it might be shifted a little bit depending on the damping. So so we can say that omega p is equal to 5. And I just estimated 5. I mean, you could say it's 4.5 or 5.6, but I'm just going to round it off. Okay, and then, so we have that. And then, let's see, from the figure here, if you look at this, we can also see the size of the peak relative to the DC gain. So here's my m sub p here. And that m sub p looks like about 10 dB. Okay, so mp is equal to about 10 dB. Okay, and if I look at this figure over here on the right, then which damping ratio looks closest to a peak of 10 dB? Right, it's somewhere between 0.2 and 0.1. And so I picked point. Well, what you should do is you should take those guesses and plug them into this equation, the m sub p equation, and then back calculate and check it. But it turns out that gives us a zeta of 0.17. Okay, so that's a good estimate. You know, anywhere between 0.1 and 0.2 is a pretty good estimate for that damping ratio. Okay, so with that then, we know that the natural frequency is equal to omega p, the peak frequency, divided by 1 minus 2 zeta squared square root. Okay, and so now I can plug in omega p and zeta here, and I'll get omega n is equal to 5.15 radians per second. Okay, so let me write that down over here on our list, 5.15 radians per second. Okay, and now look at that. 5.15 is not that different from 5, right? And probably with the resolution of this graph, you probably really can't resolve 0.1 radian per second from this graph. So, but it's good to check. Okay, it's good to verify that. Like, you know, omega p could have been 5.1 with the resolution. So I wouldn't stake my life on 5 or 5.15. Okay, but it's good to see how all that stuff fits together. Okay, so we've got that. We've got the zeta was 0.17. Okay, next is the 0, right? So we know there's a 0 that's going to affect the response. And can you see what happens here? It's got to be somewhere in this range over here, right? Because the peak, the natural frequency is over here, okay? And then the phase starts to go down, but then starts to go up. So the 0 has to be somewhere in this range, in this frequency range, to find that. And so there's a few ways to do that. One way is to look at the magnitude plot here, and I can see in the magnitude plot, at high frequency, I can see a straight line. So if I draw that, like there's a straight line like that, okay? So, and let's see, what's the slope of that line? Let's see if I go from here up 1 decade, that's minus 20 dB per decade. Okay, so that fits our model, right? We expect at high frequency, once we get past the 0, that we'll have a slope of minus 20 dB per decade. But between the natural frequency and the 0, we expect a slope of minus 40 dB per decade. Okay, so let's see, I'm not sure I see that, but maybe if we look like here, do you see there's sort of a steeper slope like that? Okay, and that might, that's maybe minus 40 dB per decade there. And then we can use the intersection of those two lines as an estimate for the zero value. But of course, it depends on how I drew those lines. So it could be really anywhere between 10 to the 1, that's 10, or 20. Anywhere in there is a reasonable estimate. Okay, so I'm going to pick that the 0 happens at, what did I use for my calculations? 13 radians per second. Okay, all right, so that's one way to do it. Okay, so it's kind of tricky here when the poles and the 0 are close together, because what happens is their effects in the magnitude plot overlap. So you can see maybe in this range here we had a small straight line, but it wasn't very distinct, and you probably could have fit lots of different straight lines in that and got different answers. If the 0 is at a higher frequency, then the solution would have followed a straight line longer, and it would have been easier to identify. So these problems are a lot easier when the frequencies are separated by a lot of spectrum, but when they're close together, it's a bit harder to estimate the values. All right, so if that's the case, let's keep going. We've got a 0 of 13 radians per second. Okay, and the last thing to figure out is the gain K. Okay, now for this problem we have a DC gain here. So the DC gain is right there, right? That's the lowest frequency we measured. That's the gain at lowest frequency. Remember in the previous example there was a slope, but there is no slope here, so there is a DC gain, and it looks to me like it's about 10 dB. Okay, so let's call that the DC gain of the system. And so what we can do is say that the DC gain that's a DC gain equals 10 dB. I've got to convert that from a log scale to a linear scale. So let's see, 20 times the log of x is equal to 10 dB. So then I'd have the log of x is equal to 10 over 20. Okay, and then I take 10 raised to the power of both of those, and I get x is equal to 10 to the 1/2, and then that gives me x is equal to 3.16. Okay, so 10 dB in the linear scale is 10 dB in the log scale is about 3 in the linear scale. Okay, so that is the DC gain in the linear scale, and then what I can do is I can set that equal to the DC gain of my transfer function. Okay, so my transfer function is k times s plus the 0, I'm going to put in the values, 13, and then s squared plus 2 zeta omega n s plus omega n squared, which is 5, let's just call it 5 squared. Okay, so then the DC gain, we cover up all the s's, or let all the s's go to 0, and we get k times 13 divided by 25. And then we set that equal to the DC gain from the plot, which was 3.16. And then we calculate for the gain k, and we get k is equal to 6.5. All right, there it is, 6.5. All right, so now we've got numerical parameters for all the coefficients in our transfer function, and so we can plug those numbers into the transfer function and write down the final answer for our transfer function. Let's do that. So k was, gs is equal to 6.5, s plus 13 divided by s squared plus 2. Zeta was 0.17 times omega n was 5, s plus 25. That's omega n squared. And there it is. We could multiply that out and simplify this coefficient, but that's good enough. All right, so that's it. That's our estimate of the numerical transfer function. Numerical transfer function estimate, right, from the Bode diagram. And as we're doing this, you're probably thinking, well, there's a lot of uncertainty here, isn't there? Like, these intersections, we sort of guessed 13 as the intersection where the 0 was. We picked 5 for the natural frequency. We estimated the peak at 10t. We're picking values off of a graph, right? And every time we pick a value off the graph, there might be some error or uncertainty in that estimate. And so you might get to this point and say, well, how good is this transfer function? How can we check? Well, one way to check is to use the MATLAB Bode command. So if I type Bode and then G, where G is defined as this transfer function, it will generate the plot. And then I can compare the MATLAB plot with the experimental plot and see how they compare. Do they overlap well? If you're good, you can actually read in the experimental data into MATLAB and superimpose the two plots together and really see how good they are. And often what we find is they might be close. We should have all the characteristics right if we figured out the right transfer function to use here, but maybe they don't overlap perfectly. So then we might go in and tune the parameters. We might change the 0. Maybe instead of 13, we might try 15 or 12 or 11. We can play around with omega n, and we can play around with zeta. Really, there's 4 parameters here, right? And we can sort of think of those like 4 little knobs, and we can sort of tune the 4 knobs and try to modify them until the theoretical transfer function agrees with the experimental transfer function as good as possible. Okay, but for homeworks and exams, this is fine. This process of doing it is good enough. But there is certainly software out there that will do this for you, where you tell it what you think the order of the transfer function is, you give it the experimental data, and then it'll do an optimization to try to make the theoretical model match the experimental model as close as possible in a root mean squared sense and give you the optimal set of parameters. But what I find is for these simple transfer functions that are not too complicated, the human can do a better job than the software can. Sometimes the software gives you strange numbers that might look right, but they're completely unreasonable. Okay, so that's the end of the example problem. We'll leave it at that, and we'll go to one more example problem. And that has to do with the hydraulic system. So when we started this section, this chapter 10 with frequency response, I showed the video of the sine sweep for the hydraulic system. And this is the data that we got from that experiment. So here's the magnitude plot and the phase plot. And we see the magnitude starts, it's already going down like this, and then it kind of rolls off really quickly somewhere in this range. And the phase, it looks like it starts at minus 90 degrees, and then it goes down, and then it seems to flatten out, something like that. Okay, so with that experimental, also you see it's not perfectly smooth like in the previous example. So this is not MATLAB faked data. This is real data in the lab. And you see there's a few things going on here. There's noise, right, in different places. Things aren't perfect. We didn't start until 0.5 radians per second, so there's nothing until that. That was our lowest frequency. There's another issue. Remember when we ran this experiment on the video, when we get to high frequency, we can see that the magnitude starts to get very small. And you can run that video and watch it again. At high frequency, the mass is vibrating, but it's vibrating at a very small magnitude. In fact, the voltage coming from the sensor is 60 dB below what it started at. Okay, that's a factor of 1,000. Okay, so if we're getting like 1 volt of position sensor signal at the beginning, we're getting a millivolt at the end. And then there's a bunch of noise in there, right? So we're hitting the noise floor. So probably what's happening here is not really reliable. Okay, so when the magnitude starts to get very small, we start to run into a noise signal issue, and I don't trust that data. Okay, so I would say that anything above maybe 40 radians per second, this is bad data, right? Bad signal to noise ratio. And we shouldn't really trust that data. Okay, so I'm going to sort of mark that off and not use that. Okay. All right, so now let's take a look at that. And what do we see? Well, first of all, we see at the low frequency there's a slope. Okay, so here we have a magnitude of -10, and then it goes down. Well, it goes down from -10 to -30 across the decade. So there's a slope of -20 dB per decade. Okay, so what causes a negative 20 dB per decade slope at low frequency? The answer is an integrator. Okay, so we expect there to be an integrator in the system. Also, an integrator will give us a low frequency phase of -90 degrees, so that agrees also. More evidence to support that the transfer function has an integrator in it. Okay? All right, but then what we see later on is that the magnitude starts to drop off even faster at a higher frequency up here. Okay, so there's got to be more than just an integrator in there, and the phase goes from -90 and then goes down. It looks like it's going down past 200, 250, something like that. You know, it might have kept going further, but because of the signal to noise problem, we couldn't really measure that. So I'm not sure what's going to happen at high frequency, but it was definitely, the phase was going down. Okay, so what draws the phase down is poles. S is in the denominator. Okay, and so so we've got that. And so let's try to write out the transfer function then. What do we think the transfer function is going to be? So here's our model of the transfer function. We think it's got an integrator in it. Okay, and then let's see, if it had one pole, it would go to 180, like 90 plus 90, but it goes past 180 phase. Okay, so there must be more than 2 poles, there must be 3 poles. Okay, but wait a minute, didn't we model the hydraulic system in the lab? Don't we know more about the system than just looking at a Bode diagram? We should, right? This is the, by the way, this is the open loop transfer function. I'm not sure I was clear about this. This is the open loop transfer function. Okay, well, that was the pre-lab. Do you remember the pre-lab for the hydraulic system was calculate the open loop transfer function? And that was based on physics, right? First principles, modeling the transfer function with physics. And when we did that, what we found was there was an integrator and there were complex poles. So because I know that from the analysis, I don't have to guess what the transfer function is. I'm going to start with that because that's what the theory told me. So I'm going to write s squared plus 2 zeta omega n s plus omega n squared, like that. Okay, and then the magnitude keeps dropping, the phase keeps decreasing. So there's no zeros that increase the phase or reduce the slope of the magnitude. And that also agrees with the theory, right? In the analysis of the lab, this is all the dynamics there were. So I'm just going to put a k and omega n squared in the numerator. Actually, I'm going to leave that omega n off, and I'm just going to wrap the numerator up and just call it k. You could put it in there or leave it out. It doesn't matter. Okay, so so that's our model of the transfer function. And again, let's make our list, right? What we need to figure this out is we need omega n, we need zeta, and we need k. Right? There's just 3 parameters here we have to figure out. All right, and so let's see how we're going to do that. Well, omega n is the frequency, is the break frequency where the slope increases. Okay, so let's go back to the magnitude plot, and I'm going to draw a line at the low frequency slope. Okay, it looks like that. And then at the high frequency slope, you see it's diverging, you know, somewhere around 20 radians per second or something like that. It's now the slope is dropping off, so let's draw another one. Now this is tricky because, I mean, it's not really that flat there. So where would you draw that line? Something like that. Oops, my darn mouse here. Okay, something like that. But again, you could put that curve in lots of different slopes because there's not a lot of data there to look at. But it's a reasonable estimate. So we should say that the natural frequency is somewhere in this range, right? Somewhere between 10, 20, and 30, right? There's 10, 20, 30. And so I picked 27, okay? Maybe I picked that because I knew the answer. I don't know. Maybe not. Okay, so I'm going to put, right, it's above 20 and it's below 30, so I think that's like 27 radians per second. Okay, so that's where we're going to put the natural frequency. Okay, that's a good estimate. Now we need the damping. Okay, now remember, it's a second order poles, and second order poles give us a hump like this. But I don't really see a hump in here anywhere. Okay, so it's not lightly damped. It's not 0.1 or 0.2 or 0.3. It's more than that, right? So we could have a damping of 0.5 or look at 0.7. There's no hump at all. Or even 1, there's no hump at all. You know, if your damping is 1, what that means is you have real repeated poles instead of complex poles, right? So you have 2 real poles that are overlapping there. Okay, so let's pick 0.7. That's a nice number. A lot of people use 0.7 because it's just kind of a nice round number. There's no roll-off. I mean, there's no hump. It's just sort of a smooth roll-off. So that's a reasonable estimate. But of course, you could probably pick, you could pick 0.5, or you could probably even pick 1, and that's a reasonable estimate. Okay, so let's pick 0.7 for the damping ratio. Okay, and then the last one is we have to figure out the gain. Now this one is tricky because there's no DC gain, right? No DC gain because of the low frequency slope. Okay, so what we did before is we went to the low frequency and we picked off the DC magnitude, or the DC gain. But we can't do that this time because there is none, because the magnitude just keeps getting larger as we go to lower and lower frequencies. So we can't do that. So we can't find a y-intercept. That means we have to find an x-intercept. Okay, so the procedure is, okay, let's just pick a value. Let's pick a frequency and then pick off the magnitude from the plot and then evaluate the transfer function at that magnitude. Okay, so let's try that. And I'm just going to pick 1. Okay, so let's use 1. So the gain, let's see, let's write it as the DC gain, I'm sorry, the dB magnitude at omega equals 1 radian per second. Oh, wait a minute. We got a units problem. Notice these are in hertz, not radians per second. Okay, so that 1 on the graph is actually 2 pi radians per second. So I better plug a 2 pi in there. 2 pi. This signal analyzer we used uses hertz instead of radians per second. That's a little bit more traditional in the signal analyzer software than radians per second. I'm not sure why that is, but that's what you usually see as the default in most signal analyzers. Okay, so the dB magnitude at 1 hertz, okay, that's here. Where's that point? That's right here, is 10 dB, or minus 10 dB, equals minus 10 dB. Okay, so that's what we got for that, for the dB magnitude. Now, let's see, we saw last time that a 10 dB was a gain of 3, so minus 10 would be 1 over 3, or 0.33. Okay, so I'll just write that, or 0.3 linear. Okay, and so now what we're going to do is we're going to take the transfer function, we're going to plug in the values we have except for k, and we're going to find the magnitude. So we're going to say g at s equals 2 pi j. Right? Remember, we let s equal j omega for frequency response. Right? And then the magnitude of that is equal to 0.3. So let's take the transfer function and replace every s with 2 pi j. So I have k over 2 pi j times 2 pi j squared plus 2. I'm going to plug in the zeta of 0.7. I'm going to plug in 27 for omega n, and then 2 pi j for s, and then plus 27 squared. Okay, well, I need the magnitude of that denominator because it's a complex number, right? So I'm going to get a j squared here. That's going to give me a negative well, I guess first I have to FOIL out this 2 pi j to all these three terms. I have to square this one, separate real and imaginary parts, and when I do that, we will get, let's see, we end up getting, let's see, how would we do that? Yeah, there's a lot of messy complex algebra in there. So we do that, we set that equal to 0.3, and we solve for k. Remember, in the denominator, we're going to get like a plus bj after we simplify this thing. And then to get the magnitude of that, we take a squared plus b squared square root there. Okay? So I'll let you finish that one up. But when we do that, we end up getting k is equal to 54. So that is the gain. All right, yeah, it's kind of complicated when we don't have a DC gain. It's a lot easier when there's a flat magnitude response at low frequency. We could just pick that off, let all the s's go to 0, and simplify that gain. But if there's a slope at low frequency, we can't do that. So we can't use a y-intercept. We have to use an x-intercept, and that's what we did here. All right, so now we have all the parameters. We can plug those in, and we get g of s is equal to... oh, it's not 54, it's 54,000, sorry. I copied that down wrong. So we have 54,000 divided by s times s squared plus 236 s plus 28561, and that's it. Close parenthesis. So there is our estimated transfer function from the Bode diagram. Okay, and again, you would ask, how accurate is this? I mean, we really guessed on like the zeta value and the natural frequency, so those might be off by a bit. And so again, it would make sense to use the MATLAB Bode command to plot this out and compare it. We did this in the lab, and we overlaid the experimental data to the theoretical data, and then you might go and tweak these, right? We think about what happens here. As you change the frequency, you move this change in slope left and right, okay? As you change the damping, you change how fast it rolls off between those two things. And as you change the gain, the whole thing shifts up and down, okay? So it's kind of like there's three knobs here, right? There's the omega n knob, the zeta, and the k knob, and each one changes part of the shape of the function. And if you think about it, really what we're really doing here is just a high-order curve fit, aren't we? Right? So we have this experimental data, we use some knowledge to estimate the structure of the transfer function, and then we're just trying to fit in numerical values for the parameters that we don't know in order to find that. Okay? All right, so you can see it's a lot harder with experimental data because the data is noisier. We had that signal-to-noise problem at high frequency, so even less trustworthy. And probably, if 5 of us did this problem, we'd get 5 different answers. The numerical values would be somewhat different, but when we plot them, if we did a good job, they should all still be a good estimate of this experimental plot. Okay, that's the end of the lecture. We will see you next time.